And this video is going to kind of talk about what limits are, and then it'll go through some kind of typical examples of what you might see in a calculus setting. So limits. Let's look at what a general statement says. This says the limit of f of x equals L as x approaches a. Okay, so this is your function. This is the eventual y value, right? The limit is just a number, and it's the y value that your function approaches when you let x get really, really close to a. You're not letting x become a. It's not f of a. F of a is just a y value exactly at that. We're looking at the limit as we get really, 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 really close to being a. So let's take a look at just a graph of what that would mean. So let's say I was looking at an x value of 2, okay, and I approach it from the left side. I'm getting really close to it. And what happens if I come from the right side? What am I getting really close to? Well, this limit is a certain y value. The point right there, whatever this y value is, 1, 2, 3, 4. And so the statement we'd say down here is that the limit of our function as x approaches 2 is equal to 4. Again, that's all a limit is. And in most, or I shouldn't say most, all polynomial cases, the limit and the function value are going to agree. So for polynomials, limits are kind of boring because the limit and the function are always going to be the same thing. That's not true for all functions, but for polynomials, cubics, quadratics, lines, things like that, then limits are a little boring to look at. They're really, really important. They form the foundation for all the things we do in kind of future calculus. But for polynomials, it looks pretty obvious that, of course, that's the limit because that is the function's value. Okay, so what does it mean for a limit to exist? What does it mean for a function to have a limit at a specific x value? Well, this is really true here. And what we're saying is the limit of the function as x approaches a minus. All that's saying is you're looking at the left. And this a plus is looking at you're coming from your a value to the right. So our a value in this case would be 2. And so this is 2 minus. It's not negative 2. It's 2 minus. It's saying approach 2 starting on the left, from the left side of the graph, and you get to there. And then 2 plus will be coming from the right side once it approaching. And you'll see on a future graph that they're not always the same thing. Okay? But this is the basics of what a limit is. It's looking at what's the y value when you look at a function as you approach some x value. Okay, so let's look at some specific limits. And again, let's look at a nice, easy cubic function. If I were to look at the limit of this function as x approaches, we'll say 1. Again, I'm looking for this. What happens if I approach it from the left and I approach it from the right? For a polynomial, well, you can just kind of plug in 1 because the limit and the function value are going to be the same thing. This particular limit is just 1 cubed minus 4 times 1, so you just get negative 3. And again, this is the y value that the function is approaching as you get really, really close to 1. Okay, what about down here? When you look at, what's the limit as x approaches, let's redo that, no arrow there, as x approaches 3. Well, if you just plugged in 3, you'd get 0 over 0, and that's an indeterminate form. We're not really sure how to handle that yet unless you've looked at L'Hopital's. But what we can do, we could look at a graph, and the graph would tell us this. There's actually a hole at 3. 3 is not in the domain. There's no way that x can be 3. You cannot find f of negative 3. The function value does not exist here. You get 0 over 0. However, we can still figure out what y value you approach from the left and from the right. That y value exists. And in this particular case, we could do L'Hopital's, which I think is probably beyond where you're at in this course, but we could just factor here. We could do x minus 3 over x plus 3, and then we could cancel the x minus 3's. Again, we're actually not going to let x equal 3. We're going to get really, really, really close to being 3. And so these two things, as long as x isn't 3, they are identical. And then as x goes to 3, this is just 3 plus 3, and we get 6. So in this particular case, we get 6, which gives us this y value, which is the limit of this function as x approaches 3. Again, approaching 3 is much different than actually being 3. X can't be 3. Let's look over here. What's the limit as x approaches 4? And I already have it graphed for you. This one is an example of a limit not existing. The limit doesn't exist, and here's why. Let's look at the left limit and the right limit. So if I approach 4 minus, that means I'm on this side. What y value am I approaching from that side? Well, I have to use this top function. When x is approaching 4, this is going to have an x value of 1. But if I look on the other side, what's the limit of my function as x approaches 4 plus, meaning 4 from the right side, start on the right side of 4 and approach 4, I get this completely different y value. Well, look at, I'm using this function now. When x is approaching from the right side, I have to use this, and I get 9. You see how the left limit doesn't equal the right limit, which means those two limits exist, right? A left limit exists and the right limit exists, but the limit, if you were asked, what's the limit of your function as x approaches 4, you're going to say, does not exist. And why? The work would be right here. The left limit doesn't equal the right limit, and you can obviously see that from a graph. We would call that a jump. We would call this a hole if you were really interested in some of the terminology. Okay, how about this example? Look at this. This is a vertical asymptote here. The limit's not going to agree. If you look at the left limit, this is going to be infinity. And if you look at the right limit, this is going to be negative infinity. Now, everywhere else on this graph, the limits are just fine. If you looked at this limit, well, it'd just be that y value. It looks like it might be negative 1. Okay, if you looked at the limit as x goes to 0, well, it's that y value. But if you look at the limit as x goes to 3 in this case, the limit of the function as x goes to 3, you're going to say it does not exist. And why? Well, because the left limit and the right limit don't agree. We can look at some of these cases, and again, there's going to be some decent amount of algebra in these cases. I'm going to go through them a little quick, but if you look and just plug in 0 here, you get square root of 2 minus square root of 2 over 0. Well, square root of 2 minus square root of 2 over 0 is just 0 over 0, and we get one of those indeterminate forms again. Okay, so what you're going to do in this case is you're going to have to multiply. You are going to have to multiply by the conjugate. Okay, so I'm going to rewrite the original one. Multiplying by the conjugate is going to get rid of those square roots, plus radical 2, and this is the same top and bottom. I'm going to do this a little fast. Hopefully the algebra is okay, but I'm going to multiply top and bottom here. Up top I get x plus 2, because the square root, and then this is a minus, and this is a plus, and those are going to cancel, and then I'm just going to get a minus 2. And the denominator I'm going to leave as is. Slow this video down if I lose you on some of this algebra here. This is just going to be, oops, that square root's not there. That was silly. This is going to be a plus 2 and a minus 2, right? Those are going to cancel. And that leaves just x over x times the square root of x plus 2 plus the square root of 2. Those x's are going to cancel, and you're left with this x plus 2 plus the square root of 2. But now you can just plug in the limit of 0, and you won't get 0 over 0. You've manipulated it that you can plug in the limit to this guy now, and when you plug in 0 for x, that goes away, and you get 1 over square root of 2 plus square root of 2, which is 1 over 2 radical 2. Again, we want to evaluate a limit. We would love to just plug it in, but if you plug it in, you get 0 over 0. So what I did is I manipulated algebraically first. I changed this thing into this thing, but then I can just plug in 0 for x or something super close to being 0 and get this. These are going to be very similar in terms of looking at things. This algebra is almost identical. If I plug in 2, I get 1/4 minus 1/4 over 0, and I get 0 over 0. But I can combine fractions, and we can simplify here. So I'm going to multiply top and bottom here by 4. And I'm going to multiply top and bottom here by x plus 2. And then they have the same denominator. And then I have 4 minus x plus 2. All over 4 times x plus 2. That's the numerator. And then this is x minus 2 still, right? That x minus 2 just went there. But then this is 4 minus x minus 2. But that simplifies to just 2 minus x all over 4 times x plus 2 all over x minus 2. And you want to notice that 2 minus x and x minus 2, those are opposites of each other, right? That creates a negative 1. So then it's just negative 1 over 4 times x plus 2. Think about that again. Hopefully I didn't do that too fast, but 2 minus x and x minus 2. If I factored a negative sign out of this, then those things would just cancel because they'd be the same. So if I cancel them, it just creates a negative sign. And now I can apply the limit as x goes to 2. Remember, I couldn't let x be 2 at the beginning. I got 0 over 0. But if I simplify it algebraically, now I can plug in 2, and I can get 4, 4, and I can make this whole thing have a limit of negative 1/16. And again, I found the limit. This is one you're going to have to think about. Again, L'Hopital's does a better job, but some people are just going to memorize that the limit of sine x over x as x goes to 0 is equal to 1. I'm going to show you a little graphical proof of it. If you looked at sine x is going to look just like that. And if you look at what y equals x looks like, it looks just like that. Do you see how sine x and x, if you zoom in here, they are identical. They completely overlap. But if the two functions are identical, when x is 0, well then this ratio has to be the same, which is why the ratio equals 1. Again, sine x and x are not always the same. If you go way over here, this value and this value are much, much different. But as long as you're really, really close to 0, sine x and x are the same, and thus their limit is 1. Okay, now we're going to kind of transfer it and go to infinite limits. Well, in infinite limits, we're talking about huge, huge, huge numbers. Not like a million, not like a billion, but like a Google. And these numbers, when you look at polynomials, are going to have absolutely no effect. Remember, this is so big, plus 4, who cares, right? This is like a trillion cubed plus 4. That's nothing. Again, this is a trillion cubed, even compared to 4 times a trillion squared. Nothing. These are just absolutely garbage. This is nothing. This is like Bill Gates, and then he drops or he gets $4 added to his bank account. Who cares? It doesn't mean anything. And so really what you're going to do on when x goes to infinity, you're going to compare the biggest to the big. In this case, 2x cubed over 5x cubed is pretty much just 2/5. And so if you looked at the limit would be 2/5. You might have to investigate that a little more, but if you're talking about a polynomial over a polynomial, you're really looking at the big dog versus the big dog. And in this case, they have a tied power. Well, what would happen if they didn't tie? Well, that's these next scenarios, okay? In this case, this is an x over an x squared. Well, this is like infinity over infinity squared. This isn't exactly how you might do it, but that's kind of like 1 over infinity, and 1 over infinity is pretty much 0. I mean, if the bottom power is bigger than the top power, then the bottom is going to be such a bigger version of infinity that it's going to dominate and you're going to get a 0. On the flip side of that, this is kind of like infinity cubed over infinity squared, which is pretty much just infinity over 1, which means that this is infinity. And so if you look at it, there are 3 cases. They can tie, like the previous page. The bottom can win, in which it would produce a limit of 0. Or the top could win, and it would produce an infinite limit. I mean, x cubed is going to dominate x squared, again, when x gets really, really, really big. We can have something like this, and again, you look to the future, but this, and again, it's just kind of fun to think about right now. This is e to the infinity over the infinity squared. E to the infinity is so much bigger than x squared, it's not even funny. I mean, think about when x is like 1,000. This is e to the 1,000th power versus 1,000 squared. 1,000 squared is nothing. 1,000 times 1,000 is a million. E to the 1,000th power is ridiculously big. No calculator can even represent it. I don't even know if I would write it, it would, take up the entire video. Okay, so this is clearly infinitely big still. And again, why do we need limits? Again, the whole point of looking at limits is to both eventually look at derivatives, because if we are not in algebra anymore, we're not going to be interested in the slope between points. We don't want the slope between this point and this point. We want like the slope at a point, and we have to look at the limit of that average slope as you get closer and closer and closer and closer. we're going to eventually find areas of curves, and we're going to approximate them with rectangles. And we can't have them have 7 rectangles or 6 rectangles. We need an infinite number of rectangles, and so we need to look at the limit as we make that width, that little bitty small delta x. We're going to make it really, 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 really small, and so limits kind of form the foundation. Okay, so I tried to take you through at the beginning of the video kind of what a limit was, how does it exist, and then I went through a decent number of typical problems, both algebraically and then some kind of thought problems about, infinite limits. Okay, this is going to get you started. I'm sure there's going to be other things you're going to have to look at, but hopefully this was an okay overview.